Let's look at how you manipulate and create tree instances. You need the tree class. Here's the part we looked at. Here's the part that makes it print out nicely. You don't need to worry about how that works. And here's an example of a function that creates a tree. In this case, a Fibonacci tree has the nth Fibonacci number at the root. The way we achieve this is to handle the base cases. When n is 0, we just make a leaf. When n is 1, we just make a leaf. Otherwise, we make a left and right branch using recursive calls. Those are smaller Fibonacci trees. And then we put them together into a new Fibonacci tree by adding together the labels of the left and right branch. Okay, so if we start Python with this loaded, then we can call fibtree. On 5, let's say, call that t. If I print that out, I see the Fibonacci tree with 5 at the root, because 5 happens to be the 5th Fibonacci number. 2 branches, one rooted at 2, one rooted at 3. We can access any label within this tree using an expression that starts with t. For example, if we want this 3, then we'd look in the branch at index 1. Here's the branch at index 0. Here's the branch at index 1. And it has a label. It itself is a whole tree. So if we don't look at the label, but instead the whole tree, we see this same structure, just not indented, because we're just looking at one branch at a time. Once you have a tree, you often want to do something with it, and that usually involves recursion, because trees have trees within them. So for example, if we wanted to count the leaves of a tree, we could process a leaf. We could write a function that takes trees, and it will be a recursive function. When writing a function that takes trees, processing a leaf is often the base case. In this case, if there's just a leaf, then the number of leaves is 1. The recursive case typically makes a recursive call on each branch, then aggregates the results in some way. What does aggregate mean? Well, it depends on what you're trying to do. In this case, we're going to get the count of the number of leaves in each branch by going through t.branches, giving each branch the name b, and calling count leaves on that branch. Now we have a list of counts which we can sum up. So in this particular function, aggregate means sum. Sometimes it might mean choosing the max or the min or returning the whole list. It really just depends on what you're trying to do. You can also write functions that create trees that are like existing trees but a little different. That often also involves recursion. For example, here's a function that takes in a tree t and returns a tree. But it's a different tree because it's a different object, and also because all of its leaf labels are 1 more than they were in t. So incrementing just means add 1. The way this function is going to work is that we'll pass in a whole tree. We'll recursively call increment leaves on each of the branches, which will give us back a new version of each branch where the leaves in that branch have 1 added to them. Those branches we put together into a new tree, and now we've incremented the leaves across all the branches, which means we've incremented them for the whole tree. Now, if the whole tree is just a leaf, then we create a new tree with the same label, but with 1 added. So when a leaf comes in, a leaf gets returned. Otherwise, we increment leaves for each branch. That means that since every leaf is in a branch, we've now incremented all the leaves across the tree. But we need to build a new tree with the same label, because this is not a leaf, and we only want to increment the leaf labels. But we pass in as the branches this new list of branches. So again, we've aggregated the result by putting it into a tree. What if instead of incrementing the leaves, we actually wanted to increment every label in the tree? It turns out that's even simpler. Returning a tree with the same structure as the input tree, but with all the labels incremented by 1, can be done by just returning a tree with t.label plus 1 as its label, and for each branch in t.branches, we increment that branch. This is recursive because we're calling increment with an increment. You don't see a base case because it's implicit. When t.branches is empty, then this list comprehension will be the empty list and increment will never be called. So in this function, t, which is a leaf, is a base case because t.branches is empty.